In a previous video, we analysed this number of neutrons n versus number of protons graph, and we said because of the short range of the strong nuclear force that this line or this graph tells us something about the stability of the nuclei in the periodic table. So if we have a proton number up to about 20, you can see that the blue line there follows the black line. In other words, those nuclei are fairly stable because the number of protons is roughly equal to the number of neutrons. As the nucleus increases, however, we lose this stability. So we can say that if we come all the way to here, these are still fairly stable, these nuclei, up to about a proton number of 83. But beyond there, we really start to see the limit of the strong nuclear force. And we say that any nuclei that have a proton number greater than 83 are generally going to become unstable nuclei. So all of these nuclei have a relative stability and would fall in the category of stable nuclei, but when we get beyond 83, you can see that blue line there. It doesn't extend any further than that point there at z equals 83. Now, in order for a nucleus to regain some stability, it's got to lose some mass, because as it loses mass, its radius decreases, and as its radius decreases, it falls back to below this line of z equals 83. Now, this natural tendency of nuclei to lose mass or energy is referred to as the spontaneous decay of a nucleus, and for different nuclei there are different time frames associated with the rate at which this breakdown occurs. So one way for a nucleus that's unstable to become more stable is to release a helium nucleus, or what we refer to as an alpha particle. Another way is that if it loses smaller amounts of masses from the nucleus in the form of an electron or a beta minus particle. Now we'll talk more about these later and where they're found in the nucleus, because it is something we haven't really discussed before. We can also have a positron emission. That means that the actual nucleus that's being decayed releases this positive or positron particle or a beta plus particle. And the third type of radioactive decay is gamma decay, or where a unstable nucleus releases a gamma ray, which is a ray of energy. And since we know that energy is equivalent to mass, then a nucleus can gain stability by also releasing energy. So let's take a closer look at these three different types of radioactive decay. So here we have our parent nucleus. Now, it's a natural phenomena for unstable nuclei to release matter because the electromagnetic force wins over the strong nuclear force, and since the range of the strong nuclear force is short, the force can no longer hold all the particles together. If we get the release of a daughter that has a smaller nucleon number and the release of an alpha particle, in this particular case, that's our helium nuclei, what we have is essentially mass is given off. If mass is given off, the radius decreases and the stability increases. So this also causes the binding energy per nucleon required to decrease, which also contributes to the stability of the nucleus. Now, we looked at that binding energy per nucleon graph in a previous video, so if you need to go back to that, have a look at it and have a think about it. So as the alpha particle is released, the daughter nucleus, which originally came from the parent, gets closer to becoming a stable nucleus. And that is the nature of the universe. Things like to become as stable as possible so that the forces are shared equally and there is some equilibrium. So we can summarize this process by writing a balanced nuclear equation. Keeping in mind that this reaction is spontaneous, it happens naturally, we can write our equation and we can show the reactant, if you like, 238 uranium, which represents the parent, so that's that one there. It has 146 protons and 146 neutrons and 92 protons, giving us a total of 238 nucleons. Now, the daughter has 4 less nucleons, because obviously there are 4 nucleons in a helium nucleus, 2 protons and 2 neutrons. Now we can write the alpha particle as 4,2 helium, or we can write it as 4,2 alpha. Now we can also check our balance by considering the law of conservation of matter, and since this represents the spontaneous decay, there really is only one reactant, and if we add the proton numbers, they should be equal on the left hand side and the right hand side of the equation, and the same goes for the nucleon numbers. They should be equal, so all protons and neutrons are accounted for. Now, this is a spontaneous equation. In a previous video, we looked at an induced nuclear equation or reaction using something like 235-92 uranium and bombarding it with a neutron. You can see the principles are similar, but this will not happen naturally. This one needs quite a lot of energy. It needs a high kinetic energy neutron to cause the splitting of this nucleus, which then produces the 2 daughters and the 2 neutrons. So another type of decay happens as a consequence of not the strong nuclear force weakening, but the weak nuclear force becoming unstable and therefore producing an unstable nucleus. Now, beta decay, or in this particular case beta minus decay, which represents an electron, is an example of a spontaneous decay reaction that results due to the weak nuclear force, as opposed for alpha decay to the strong nuclear force. And if we think about the unstable nucleus here, the proton number is still greater than, but closer to 83 than, let's say, a uranium nucleus, which has a proton number of 92. So the release of an electron or a beta minus particle comes from the spontaneous decay of this nucleus, and we say that the weak nuclear force is responsible for this. Now, one thing we haven't talked about is, where does this electron actually come from? We know there's no electrons in the nucleus. Well, but is there? Well, there is. So here is a neutron. Now, this neutron is made up of 3 smaller particles. Don't worry about the naming of these particles at the moment. This is a proton, and within the proton there are 4 parts. 3 of them are called quarks. So we have our negative quark, D representing down, and so obviously if D is down, positive is going to be up. We don't have to worry about that now. We'll come back to it when we look at the standard model in Year 12 physics. And the squiggly line represents the weak nuclear force, so that represents the attractive force between the quarks. So when we have beta decay, what happens is an electron is released from a neutron, and that means the quark that's released is negative. So this leaves the actual daughter nucleus with an extra proton number, because all of a sudden now that neutron has become a proton. And another particle is released again. We're not going to focus on this at the moment. We'll come back to that in Year 12. This is called an antineutrino. So we say that one neutron becomes a proton. Why? Because it loses a negative quark or an electron. And an example of this is the spontaneous decay of radioactive carbon. Now, we know that there is a small percentage of radiocarbon that is this 14,6 isotope. The reason it's 14,6 is because it has an extra 2 nucleons. And when this carbon decays spontaneously, you can see here the proton number actually increases, but the nucleon number stays the same, and that's because an electron or negative quark has been released from the neutron. So if we were to write a nuclear reaction or an equation representing this beta minus decay, or this electron decay, then we use our conventions, A being the atomic mass number or the nucleon number, and Z being the proton number or atomic number, X being the element. So you can see here the proton number increases by 1, and if we apply our conservation of charge and our conservation of mass, what we've got here is this number here, which should give us this number here. So if you take that 1, it leaves us with a Z. And of course, the antineutrino has no charge, no mass. So this represents that a neutron, which is made up of the 3 quarks, changes to a proton because one of the electrons is gone, leaving it with a net positive charge. And we have this beta minus particle. Now, an example of this, if A is equal to 14, which is, let's say, our carbon 14, Z is equal to 6, so that's our carbon 14 isotope, then Z plus 1 would be 6 plus 1, which is 7, giving us 14, 7 nitrogen, which is one of the daughters, which happens to be a different element totally, because the proton number has changed. And let's face it, the proton number determines the type of element, and 14,7 nitrogen is a more stable version of the 14,6 carbon, and that is the purpose of spontaneous decay, so that the actual nucleus finds its optimum stability. Another kind of beta decay is beta plus decay, which means there is the release of a positive quark or a positron. So we call this a positron, and also a neutrino is released. Now the chemical symbols that we use, or the nuclear symbols that we use, 0 positive 1 electron, so there's your electron, but it's positively charged, making it a positron, and 0 0 neutrino. Now, an example of this beta plus decay is if we take this isotope of carbon. In this particular case, we've got 10 6 carbon, so proton number 6, nucleon number 10, and one of the actual neutrons releases a positron. That means it leaves the nucleus with 1 less positive charge, turning it into a 10-5 boron nucleus. Here is the release of the positron or beta plus particle, and of course the neutrino. Just checking our balancing again, as we do: conservation of charge, conservation of mass. And of course we check our nucleon numbers on both sides of the equation. So the proton number in beta plus decay decreases by 1 as opposed to the proton number in beta minus decay increasing by 1 in the daughter. And if we were to write that as symbols, what we have is the nucleon number remains the same, but the proton number increases by 1 because the nucleus again tries to form a more stable nucleus, and by releasing this positron it achieves that purpose. Now, the chemical equation that we would write, similar to the previous example we looked at, you can see here the proton number actually decreases by 1, Z minus 1, and we have this positron and neutrino that's actually released in beta plus decay. So the last kind of spontaneous decay is this gamma decay. Now, gamma decay results in the release of pure energy like light. We call that a gamma photon. So this is a high energy photon, unlike light, and the nucleus goes from one nucleus, which is called an excited nucleus, to a more relaxed nucleus. Now, this relaxed nucleus has greater stability. Now, we know that according to Einstein's energy mass equivalence equation, that whether you lose energy or whether you lose mass, because they're equivalent, it's going to produce the same result. So the stability can be increased by, or can be achieved by, losing energy as opposed to losing mass. So there's no mass that's released here, but there is these gamma photons that can be released. Now, what that results in, what does it mean, a more stable nucleus? Well, it means it has a lower binding energy per nucleon value, and it also has a greater mass per nucleon value. So we said that the mass of a nucleus depends on which nucleus it's in. When a nucleus becomes more stable, the mass of a nucleon actually increases.